Hi. Hi. But just so you know, your voice will be streamed out, but it's okay. Okay. Oh, of course, of course. Yeah, it's just not yet up on the sheet yet. Uh-huh. Ah, right, right, right. Yeah. Uh-huh. Right. Yeah. Uh-huh. Okay. Good. It's working. Uh-huh. Bye. All right. Morning, Yuhao. Li Jun, Liang Yu, Yaqing, Jessica, and Justin, and Yanjun. And bonjour, Celia and Chimao. So I actually like the weather today. It's misty. Checking out the squirrels, the birds, okay, and the kids and dogs casually walking around the lake. Hi, Livia. So maybe after the lecture today, Polly will go get lunch and then walk around the lake a little bit. Hi, Ida. And you know what? The bell rings. So let's go ahead and start. So, well, there are no more to do except for the ones that we mentioned yesterday. Okay, just a little bit ahead, looking a little bit ahead. PA7 and exam 2s are coming up the next week and the next week. Today, we'll talk about TCP's reliable data transfer more extensively. Okay, yesterday you heard that all those RDTs, whether it's 1.0, 2.1, or 3.0 we talked about, those are general mechanisms. Okay, in those RDTs we count packets one by one, and we call packet 1 sequence number 1, packet 2 sequence number will be 2. But in TCP, we don't count these data one packet at a time. we count actually 1 byte at a time. Okay. What's also unusual is that in those RDTs, we assume a simple case where one side sends data only, the other side sends acknowledgements only. But in TCP, hey, one side can be the client, the other side the server. What happened there is that client might be sending request messages, server might be sending response messages. Both of these messages are real data. So in a way, the two sides in a TCP connection is not exactly just one way, it's bidirectional. Data can go this way and data can go that way. So you see that data go this way. As data go back the other direction, acknowledgement also go back to acknowledge the first data. Similarly, the subsequent data coming from this end might also carry acknowledgement for the data coming back from the server. Okay, so you will be seeing packets flying two directions, both carrying data sequence number and the acknowledgement sequence number. Okay, so the video here coming up very important. It's to set the stage, explaining all these interactions.
TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Yeah, let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right? Each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on, so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to what? Break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? The byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you, TCP implements, just like go back in, cumulative ACKs. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet. But now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly, to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so ACK number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go backend. So if you recall, go backend's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them.
So interesting, isn't it? When we were talking about go backend RDT, we say packet arriving out of order, discard. But to be realistic and conserve bandwidth, they now can buffer out of order packets in TCP, kind of go back in. Next, let's hear examples.
Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in a telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Okay. Now because it's a very straightforward character C, not like escape or Control C, therefore what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number will be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number. Yeah, the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? The last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, yeah, we say ACK 43. And this is also host B telling host A what is the next data byte expected. And therefore we see the next packet coming back from host A, sequence number 42. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So add packet needs to be what? Last byte received by host A, which is 79 because there's only one byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction.
And that takes us to the first quiz today. This is number 23. Let's exercise counting bytes in a TCP connection. So let's consider a simpler scenario on the left. Host A, host B. A here sends a packet to B. It starts from sequence number 42 with data 7 bytes. You can imagine B sending back an acknowledgement saying 49, isn't it? And host A can send further data starting from 49, and let's say that it sends 3 bytes of data. The acknowledgement will then carry the number 52. You see also that an easier way to calculate the acknowledgement for a data packet will be simply sequence number plus size of data. Okay. Now let's consider a realistic scenario. That's the scenario on the right, and that's where the questions are. Okay. Host A and host B, they are sending data both directions. Oh, no problem, no problem. So host A here sends a data of 10 bytes, starting from sequence number 42. Then you can probably imagine what value of B will be, right? Because this data coming from host B to host A next should acknowledge this data. Okay. And as B is also sending 20 bytes of data back to A, what should be the sequence number of this packet? Well, you check the acknowledgement number there from the packet coming from A, right? That indicates what's the sequence number that's expected. Yeah, so A is quite straightforward. But what should be the value of B? Okay, once you get A and B and the size of the packet coming from B to A, can you derive C and D? That's the third packet coming from A to B. And can you also derive E and F in the fourth packet? Okay, that's coming from B to A. So quiz 23 is asking you to tell the value of A, B, C, D, E, and F. And spoiler alert, guys, Boris has already posted the solutions they have. I would actually suggest that you guys go ahead and work on your own instead of overlooking other people's, because that usually prevents you from really exercising what you were learning. Okay, so let's take some time. You know what? Polly will work on it as well. So A should be, and B should be. Okay, so with A and B, A and 20, then I know D. Okay, good. With B, I know C. Okay, good. with C and 0 by, I know F. And then D being, so I know that E should also, okay, good. Okay, now I can check whether Boris and Weiyo, whether you guys are getting things right. Okay, so A, B, C, D. Good. E. Yeah, you know what? Boris is right. And yes, Team 4 is also correct. Yeah, Team 7, that's a perfect solution. Good. So you see, I can tell from Team 7's solution that they totally get it. Okay. Yeah, 加油. Very good. Okay, Yuting, there you go. Shuquan, Team 3, sure. Okay, good. Looks like we are all getting it. Not that hard, is it? Because it's a little bit different from RDT, but now you get it. Yeah, Chima was wondering how you type so fast. I guess you guys can actually start typing. Well, no, maybe. I think Boris. Trade secret. I think Boris, you probably collected also the old quiz questions. I guess that's it. I got a pattern. All right, good. So, guys, very good. Very good. Okay, Team 6. All right. Yuxiang. Okay, very well done. Good. And we are good to go on to the next topic. Well, we are set up to talk about the finite state machine, but there's something else I want to talk about before the finite state machine, which is the timeout interval. If you recall in RDT 3.0, in order to address the issue that a packet can be lost entirely, so you don't get to do the checksum and see if there's an error bit and send NAC, because you don't get it at all. So at the sender side, there's a mechanism. After we send the packet, we start the timer. When the timer times out, we retransmit. Because during that time, if we don't see any acknowledgement coming back from the receiver, chances high the packet is dropped somewhere. Okay. Now, the tricky part we talked about back then was to set the interval for this timer. Let's see, TCP being a real mechanism that's working, there must be a way they calculate, okay, or estimate what the timeout interval should be. So this will be the next two videos about, and let's start from the first one.
Now with the fundamentals of TCP packet format, TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before Polly shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If and ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical, and that interval determines how long the retransmission is going to go, and that influences the performance of the reliable data transfer. We know already in some earlier example, if that timer is set too short, yeah, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, yeah, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard Polly saying this already. The interval should at least cover what? Time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard Polly saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round trip time repeatedly in between the pair of sender and receiver. And this is exactly how it's done. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a simple RTT. Now, there will be a lot of these simple RTT for each data and ACK pair, but we will ignore the data ACK pairs due to retransmission. So some of these data might get lost, and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these simple RTTs, and they could vary quite a bit. So you see that it's actually not good to use the simple RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent simple RTTs. So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smoothed RTT next is going to be the smoothed RTT now, and take a weighted sum of that to the current sample of RTT. Okay, so current smoothed RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average, and we're using a special factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current smoothed RTT. Now, this whole thing is going to be used as what? the first term of the next estimation. So you see, okay, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay, 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Okay. Oh, and by the way, alpha is only 0.125. That is because, we don't want to weight too much on the instantaneous RTT, because otherwise it will be what? Also fluctuating, okay, not exactly smooth. And here shows, the instantaneous RTT and the estimated RTT, the smooth estimation, how they look like relatively. And this is actually actual measurement between UMass and Eulercom again. Okay. So the blue one that fluctuates more, like these. These are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smooth, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, relatively smooth. And you see also, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, the smooth average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. But the estimated RTT there is certainly not covering most of the round trip time observations. So there's more. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. And the timeout interval should be the average plus a safety margin there, such that all these simple RTT fluctuates in the middle will be covered. Or, the more simple RTT being covered by the safety margin, the better. Challenge next is to set the safety margin. And the thinking behind setting the safety margin is this. If the simple RTT fluctuates a lot, we use a larger safety margin, right? Small fluctuation, smaller margin. Therefore, the key is to estimate the variation of the simple RTT. So the challenge boils down to estimate the variation of simple RTT. And that can be done this way. So simple RTT is the instantaneous RTT. And estimated RTT there is the variable storing the average RTT. So the deviation is essentially what? The simple RTT subtracting the average RTT. Right? Now, of course, we will not be using this, by itself to set the safety margin, because this is also what? The instantaneous deviation. Right? So let's estimate the smooth deviation of round trip time, by the EV-RTT, and borrowing again the technique, the exponential weighted moving average, to get the smooth depth RTT. So the next depth RTT will be the current depth RTT and the weighted sum of that to the instantaneous deviation of RTT. Alright, so the only thing left is just the beta factor, and it's also set to a small value so that we weigh less on the instantaneous deviation. As to why it's 0.25, not 0.2, not 0.125, these alpha beta values are usually given because people have been using these values and they seem to work out fine. And engineers later on will just borrow using the same setting. And now finally, the timeout interval. It is the estimated on-trip time plus the safety margin, which is determined by the deviation of round-trip time. Now as to why 4 times the deviation of round-trip time, the original designers of TCP, they don't usually talk about this. I mean, the 4 could be a result of repeated experiments, but Poly guessed also it could be because of this. They have assumed the simple RTT distribution being normal. If you recall back in Statistics 101, right? Normal distribution is for a sample such that if you plot the histogram of that sample, you see a bell shape. The average is usually in the middle where there are lots of samples, and the 2 ends, few samples. In normal distribution, starting from the average, if you add 2 standard deviation, subtract 2 standard deviation, it should cover what? 95% of the value range of all these samples. So by adding 4 standard deviation here, timeout interval here is covering more than 99.99 something percent of these sample RTTs. That is also saying, setting the timeout interval this way, there's going to be very few premature timeout in TCP.
Okay, good. So you see the entire suite doing computation to get the timeout interval. And now we are ready to start TCP's RTT finite state machine.
And here, RDT of TCP. These are the characteristics. First of all, it's pipelined. So we send packets back to back in TCP as well. We could have multiple packets in one flight. And the acknowledgement is cumulative, meaning the sequence number in the ACK indicates all the packets below that up to that number are received correctly. And there's only one retransmission timer for the entire flight of packet. And so when that timer times out, then we retransmit the flight of packets. So up to this point, you will probably guess TCP's RDT looks very much like, GBN, the go back in. Now the slight difference is this. In TCP, the RDT adds a little bit something so to speed up the retransmission. And that is a special condition when the sender sees a certain number of duplicate acts arriving quickly. Retransmission timeout, that's not wait for that, that's quickly retransmit. Okay, so this is also called the fast retransmission mechanism. So this is something that's a little bit unlike the standard go backend, but implemented in TCP. Right. Next are the finite state machines of the TCPs. To make it simple, let's ignore the dupe ACK part, okay, the fast transmission part, and let's not talk about the other mechanisms we have not yet discussed that's implemented in TCP. If you are expecting TCP sender looks very much like go backend sender, you're correct. First transition is what? The get call from above transition. Okay, receive data from application. Okay. So in TCP sender, we generate the packet, assign the sequence number to the packet, of course also calculate the checksum, and pass that to the lower layer. So it's essentially the UDT send call. And we check whether the timer has already been started for the flight. If it does, don't do anything. Otherwise, if there's no timer currently running, we're sending a packet, then this must be the send base. Start the timer. And then we increment the next signal. But in TCP, we are not counting packets, right? If we are counting packets, we add the sequence number by one packet. But here, we are counting the bytes. So we are adding the number of bytes in the data in the packet we're sending out. Now, you see here, I'm trying to be a bit lazy. I did not do the window size check, okay? But in TCP sender, there's also a window size. So there should be a if condition here before creating packet to check whether the next seed num, okay, is still within the window limit, of course. And next, yeah, this is also a familiar transition. This is the transition when the sender receives an ACK. Well, similar to Go backend's transition receiving an ACK, that's extract the sequence number from the ACK packet. Now, the action of TCP sender here is different. Only when the sequence number is larger than the same base, meaning this is a new ACK packet. So the sequence number here is something that has not yet been acknowledged. Then we set the same base to the new sequence number because now acknowledgement is received. Sender should say that that's slide the same base over. All right. Now, if there are currently not yet ACK packets around, then that's restart timer. So we'll be starting the timer for the new send base. If there are no outstanding packets, so if there are no not yet acknowledged packets around, then let's simply stop the timer. Because this ACK here, yeah, acknowledges all the packets that are waiting to be acknowledged. All right. So, hey, looking very simple. That is also saying when y here equals the send base, we do what? Nothing. So if a duplicate ACK is received at the TCP sender, hey, timer does not get restarted, unlike in Go backend. Yeah, even though the sequence number is the same, timer gets restarted, refreshed. Okay. And the third transition, again, very typical, this is the timeout transition. So when timer times out, retransmit the entire flight of packet from the send base, and then start timer. This is actually identical to Go backend. Yeah, in Go backend sender, there's actually one more transition, which is doing what? Checking whether the ACK is corrupted or whether the ACK is a NACK. Okay. In those cases, we do nothing. But you see, yeah, when ACK is received, do these. And when the ACK is new, is doing this. So all these other things do nothing, is just, saying default actions all ignored. Okay, so from now on, if you don't see any other conditions being listed as a transition here, that means they will be just ignored. Now, this is just another way of writing the finite state machine, but in a pseudocode form. So we switch, different events. There's the data received from above case. There's the timeout case. There's also the receiving of an ACK packet case. So receiving data from ACK, generate packet, set the sequence number in byte count, and start timer if there's not one yet running. Just to make sure that you set the timeout interval to what? The estimated RTT plus 4 times the deviation of RTT. In timeout here, if it is triggered, then retransmit the whole flight of segments and restart timer. Receiving an ACK, extract ACK number. If the ACK number is new, meaning it's acknowledging something that has not yet been acknowledged previously, then update the same base. So we slide the window over. We restart the timer if there are still unACK packets waiting. Otherwise, stop timer. These are the only 3 events. If there are other events occurring not fitting any of these events, ignore. If you're not quite convinced the previous slide is a pseudocode, this one should convince you. Okay, so what I'm listing here, typing up here, is essentially what the finite state machine is telling. Initialization, and this, yeah, it's gonna go forever. It's looping forever, just like every server here, right? Waiting for an event to occur and take the actions correspondingly. It's a switch essentially on the events. And there are 3 different events: getting data from above, timeout, and receiving an ACK. So from a finite state machine, you can actually convert it to a pseudocode, give this to your programmers, then you get yourself a TCP sender implementation. Right. So, being able to write out from the thinking, from the designing of TCP sender to the finite state machine is essential, because that drawing the finite state machine out of your thinking process is simpler. Okay? Trying to write the pseudocode out of the thinking process, just too challenging. Okay? Once you get the finite state machine, then you can gradually transition that to pseudocode. And there, you are one step closer to getting an implementation of what you were thinking about, what you were designing about.
Okay, so now you see that finite state machine that we keep drawing, it's graphical, but it's actually not that far-fetched in terms of trying to write a program that's based on that graphical model of how we do reliable data transfer. Okay, so from the graphical model, you can actually write it in a form of a pseudocode. And from there, you can see how you can program TCP sending side, isn't it? Similarly, if you take the receiver finite state machine, turn it into pseudocode form, and then you know how to write the receiver side of TCP. Now let's just do the last bit of reliable data transfer finite state machine, which are 3 examples.
As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data sender here. Host B is just receiving, sending acknowledgements. Host A here sends 1 packet starting from sequence number 92. And it's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay. So, host A here waits until timer fires. And so, the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. Right, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, we are trying to demonstrate the strengths of using cumulative ACK. That is here. If one of the back-to-back packet that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So to this point here, sender host A here seeing ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back X, okay, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short, so timeout occurs before X can come back. So first, timer occurred here. Therefore, timeout event in TCP sender's trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Okay. Now, Act 100, Act 120 will arrive later. Okay. So when Act 100 arrive at the sender here, Y equal 100, that is the sequence number in the Act. The send base at this point is still 92. So Y is greater than send base. Therefore, we change the send base to the new Act number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, hey, timeout occur, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here, we restart the timer, and this timer is associated with send base 100. When Act 120 arrive here, we need to change the send base because it was previously 100, and the Y is 120, bigger than 100, so change the send base, slide the window over. Do we stop timer or restart timer? There's no more outstanding packet because there are no more getting called from above. Okay. So, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver, receiver is going to see, data byte up to 99 received. But the thing is, receiver has already received up to 119, so those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded, and an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when Act 120 arrives at the sender, well, Y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the 3 transitions, we ignore it. Sender does nothing. The second packet here, with sequence number 100, will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, 100 to 119 bytes have already been passed up to the application layer. So another ACK, 120, is going to be sent back to the sender. And sender is just going to ignore it again.
So that was TCP's example in 3 of them. We take a break, and afterwards we'll come back to sum up the finite state machine of TCP and talk about 2 more hacks to try to improve the performance. And then we'll talk about the rest of TCP, the flow control and connection setup, connection teardown. And then we'll be off for the day. And we'll also be off for the reliable data transfer part of TCP. Okay. Good, so let's break for 10 minutes and I'll see you in 10 minutes. right, so let's sum up TCP's reliable data transfers finite state machine. And that's a slightly longer video, 8.5 minutes, because we need to talk about a very special transition, the timeout transition, a little bit more.
And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay, the examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also, explains in example 3. You'll see in the textbook, the authors will describe it this way. When the send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back, in go back in, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. The description in the finite state machine says this: retransmit not yet act segment with smaller sequence number. Now we read down the actions being taken carefully. You see, this is not in the pro form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back in. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of condition control. That's defined more precisely what TCP sender does when there is a timeout event. Know that this is no longer the simplified TCP. This one is actually quite realistic considering condition control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting 1 segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way: 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, at the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round trip time plus 4 times the deviation of the round trip time. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh wow. We were actually quite conservative here already, isn't it? That is what? Covering 99.99 something percent of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this, window size dropping all the way to 1 and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more ACKs coming back. That is probably because data cannot go out. But TCP being a pipelined reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of ACKs, or maybe seeing some duplicate ACKs, old ACKs coming back. Not that we get no ACKs at all and eventually run into timeout. So timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down by reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposedly if this is go back in, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus a go back in. So we see similarity being what? Both of them are pipeline segment, and both use cumulative ACKs, and there's only one retransmission timer, and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. In go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay, so exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously.
All right, good. And you might notice until now, right, the finite state machine we talk about is strictly the sender side. We'll be talking about the receiver side here. And here you will hear that TCP's receiver is a little bit unique. It's not sending one data, one ACK. It's actually sending ACK in this very special way called delay ACK.
This is the delayed ACK. So this is the mechanism implemented at the TCP's receiver. Now, in order to contrast TCP's receiver to go back end's receiver, let's bring back go back end receiver's finite state machine. And here it is, the go back end's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it up to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go backend does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go backend's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. We're supposed to generate ACK and send the ACK back. But at TCP's receiver, okay, how we send the ACK back depends on the second condition here. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed. Yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. So, if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. So that's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, let's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a back packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay, the similarity, however, is more the action being taken. Okay. So when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay. Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Okay. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. Okay. The sequence number in the ACK here will be still the latest packet arrived in order. So this will acknowledge all the packets before that.
How does that work for you? It should be fairly clear. There will be a quiz coming up, but after we talk about this second improvement, it's called fast retransmit.
Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we're describing, when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice. the current value. Okay? Because TCP sender, they actually consider a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here being a pipeline RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any ACKs coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out did not hit congestion point? Okay. And we just have a random lost packet in the middle of it. What does the receiver do there? Yeah, it's gonna get packet in order and then a random loss. All the subsequent packet arriving out of order are gonna generate duplicate ACKs coming back to the sender. If you recall TCP sender, when there are duplicate ACKs, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate ACKs, and when there is a hidden number of them, then you will probably guess there is a random drop right before the duplicate ACKs, okay? Or at the first unacked segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple ACKs for the same data, to be more precise, it's triple duplicate ACKs. Then we resend the unacked segment with the smallest sequence number because this is very likely the lost packet there. Okay. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. Okay? And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate ACKs coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate ACKs. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate ACK for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same ACK back to back. So sender here received the first ACK for 100. And this is the first duplicate ACK, second duplicate ACK, the third duplicate ACK. And this is when we begin retransmitting the first, the smallest sequence number that is unacked. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an ACK packet from below. Okay. First of all, we extract the sequence number in the ACK packet. And this is the case when the ACK packet is new. And this is the other case when the ACK packet is not new. So in here you see, we increment the count of duplicate ACKs. Okay. For each duplicate ACK, we increment this by 1. When the count for duplicate ACK is exactly 3, then we resend the segment. So this is fast retransmission of a lost packet. And then of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there is a new ACK. When there is a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see when there is a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP are these. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout.
So that's TCP's RDT. And that takes us to also the second quiz today. So guys, wake up. So this is number 24. So you see go back and receiver before. Go back and receiver is relatively straightforward. But what is TCP's receiver finite state machine? Okay, so what I'm showing here is TCP's receiver with the delay ACK mechanism. Okay, so you see that there are, more transitions. Okay, let's focus on the transition on the lower right. That's called T1. Can you recognize what this transition is handling? Well, first of all, let's look at the condition, okay, that's triggering T1. RDT receive, so we are receiving a packet, and it's not corrupted, and it does have the expected sequence number. Okay, so in order, everything is good, okay, but it's checking one more thing. Does it fill the gap? If it's not filling a gap, okay, and there's no data pending, okay. There are 4 events, okay, the TCP receiver triggers, okay, and which one is T1? No packets pending. Yeah, so that's the first event, right? We'll be generating an ACK, but we will also be starting a timer, 500 millisecond. Only when the 500 millisecond times out, then we send the packet out. Send the ACK packet out. So T1 there corresponds to event number 1 in delay ACK. Delay ACK TCP receiver. Yeah. What about T2? Okay, let's check also the condition of the event. Receive a packet. It's not corrupted. It has the expected sequence number. Okay, very similar to T1, isn't it? But it differs here. Is it filling a gap? It's not. So it's a new packet, okay, brand new. And, there's a packet pending. Yeah, so this is the second event in TCP's receiver. Okay, what do we do there? We extract data, deliver it up to the application layer, and generate the ACK packet and send it out immediately. Okay, so this ACK packet carries the sequence number of this packet just arriving. And of course, we'll increment the expected sequence number and say that pending is no longer true, right? Because once we send an ACK, then it's all clear. If there's another packet coming, then we should be waiting. So pending now is false, so that will be triggering the receiver to go to T1 because there's no pending event. Okay. At that point, we also remove the 500 millisecond timer. Good. So T1 is event 1, T2 is event 2. What is T3? T3 says, oh, default, and simply send the acknowledgement packet that has been previously generated, and then reset pending to false. Okay, and then remove timer. Which event does this transition correspond to? Okay, hey guys, this one is a little bit tricky. Okay, I'll let you guys figure it out. T4, on the other hand, let's see what it does. It's triggered when we receive a packet and the packet is not corrupted. It has the expected sequence number. Oh, but it fills the gap. If that's the case, we extract data and pass the data all the way to the latest data that we receive in order, right? So this is somehow a retransmission of a gap earlier. And we generate an ACK, and the ACK is also all the way to the end of the sequence number received in order. And we send the acknowledgement immediately. Okay, increment the sequence number, reset the pending to false, and remove timer. Yeah, you guys are right. That's even number 3, number 4. I actually forgot. I think it's even number 4, right? The case where we fill in a gap. So T3 is still a mystery. Okay, but don't worry. Let's work quiz 24 out. Q1 asking something that's a little bit simpler. Which of these 4 transition is delaying acts? Okay, so this is easy. Q2 ask, which transition sends new acts? Oh, which transition sends new acts? Okay, this one is easy for many of you, but some of you might also see, oh, this is a trick question. Q3, which transition sends duplicate acts? Okay. When do we send duplicate acts? So we are resending an act that has been generated previously. So which transition is sending duplicate acts? Think about it. Okay, so Q24, quiz 24, Q1 is straightforward, but Q2 and Q3 does require a little thinking. Okay, and maybe going back to the slide about the delay act. No worry, you guys will have time to think about it. And again, spoiler alert. Okay, maybe look at the video screen first before jumping to Slack space. Oh, okay, so there's a question. What is a new ACK? A new ACK is an ACK that is not a duplicate. So it's an ACK that the first time we see the sequence number. Yeah, I had a feeling that you guys are a little bit stuck in Q2. Q1 is straightforward, isn't it? Good. Must be T1. In fact, Q3 is also not that hard. Okay, so Q3 is the case where we receive packets that's out of order, creating gap. Okay, so T1, T2, and T3 are all packets arriving and as expected. Therefore, out of order packet will definitely trigger T3. Okay. So T3 there is the one generating the duplicate ACKs and the only transition that's generating the duplicate ACKs. Now, Q2 I understand, it's a little bit tricky. New ACK. Well, we see, right, T2 and T4, they're generating ACKs and sending them out immediately. Okay, and these two transitions, okay, are receiving packets as expected. So you're moving the sequence number forward. So T2, T4, you know for sure, are generating new ACKs. But are these the only transitions generating the new ACKs? Yeah, I see Sheng Wei, Team 15, says, hey, obviously T2, T4. And I think Li Jun says T2, T4. Very good. You know what? You guys are right. Okay. Either Team 10, you guys got it? Yeah, I know. As I was describing the quiz, I said that Q2 is a little bit of a trick question. Okay. And so, hey guys, Team 2, 6, 4, 1, 10, and 12, and 15. Hey, no need to feel that you are making a bit mistake. No, it's not. It is a little bit tricky. There's one more situation we are generating new ACK, which is this. Look at T1. Sorry that I actually do this on purpose. When I'm talking about T1, I did not go through all the actions. The actions are what? We extract data, deliver it to the application layer, we generate the ACK. But what? We start timer. Yeah, there's a chance the timer expires. Okay. When the timer expires, we'll be triggering a timeout event because there's no timeout event here except the default, which is T3. So when there's a timeout, T3 is triggered. And yeah, that new ACK we generated in T1 will be transmitted. Yeah, so we then change pending to false and remove the timer. Okay. So the special characteristic in the finite state machine you look for to make sure that you are also sending new ACK is setting pending to false and remove timer, which you see not only in T2 and T4, but also T3. Yeah. So for Q2, yeah, Boris somehow knows the answer already. You did not get tricked, okay? But I think you have your information source, okay? Really insightful. That's good for you. Does it mean that duplicated old? Yes, Celia, yeah. By all ACK, I meant the duplicate ACKs or all ACKs. Okay. Yeah, all ACKs are duplicate ACKs. New ACKs, fresh, okay, not a duplicate one. Now with this quiz, you can also clear the terminology. Great. Very good. So you see team 15 here, correcting the solution by saying, hey, we could also combine T1 and triggering T3. Therefore, we see a new ACK. Yes, Shanting. T3 also sends new ACK. When does it send new ACK? It's sending new ACK when there's a T1 being triggered before, and there's no more data coming in for 500 milliseconds. So that ACK generated by T1, after 500 milliseconds, that ACK packet will still go out. And which transition is to force that packet to go out? So the timeout event belongs to the default transition. That's where that new packet that waited for 500 milliseconds goes out. Very good. Very good. Okay, good. Yeah, I see you guys editing it as well. Very good. Yeah, good. Yeah, I think you guys are getting the receiver side of TCP's RDT as well. Okay. Sender side clear. Now the receiver side. So they are obviously more complicated than go back ends. Later on, next week we'll talk about congestion control. You'll see that TCP's sender receiver go back finite state machine gets even more complicated. Okay. Yeah, with the rest of the time, okay, let's try to close TCP's reliable data transfer. And the next topic is this, the flow management or flow control.
And that takes us to the flow control of TCP. Allow me to explain. So this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. Okay. If everything is okay, TCP receiver is going to extract data and pass it further up. What's going on really in the implementation, in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Just like the TCP receiver here is going to push more data into the receiver buffer. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more. Because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So full control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined. And it's actually the size of the receive buffer space. Now, initially, RWND is going to equal the receiver buffer. whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher.
And the last video today. So we'll actually end about 1 minute or 2 minutes over the regular time. Bear with me. Let me borrow 2 minutes.
Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay? At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay? So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, okay, that needs to be initialized. Okay. And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seek num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose an initial sequence number to tell the receiving of the request messages. And it's gonna be sent in a TCP sync packet or sync message. Now if you recall back in TCP packet format, in the header part of it, there are a number of these flags one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere. Okay, and that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now, the server will then in the sync received state. So, server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. Okay, so sync ACK is such a packet. That is to ACK, receiving the sync packet. Right? The server here will be doing yet another thing. Okay, choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. Okay. And in sequence number, server tells the client it's going to start from Y. Okay. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is X plus 1. All right, so next seek num is already set to X plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. Okay? And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. Okay? So it's just an ACK packet, and the ACK number is Y plus 1. Because this guy here observing the initial sequence number of the server is Y, then therefore the next seek num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close, and ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Okay. Then it's going to enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Okay. Server here receiving the fin packet sends back an ACK. Okay, so ACK bit on, and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Okay, some more ACKs waiting to come back here. Okay, so server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin is pretty much done, and just waiting for the server to say everything is already sent, so you're okay. So finally, server says, done with all the data. Okay, so sending fin. Client here is receiving the fin, sends back the ACK. Okay, saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until you can really close the connection?
All right, you know what, guys? That's all for today. Okay, go get lunch. I see that one more team has addressed quiz 24. Okay, next week, come back. We'll break open a new topic: condition control. So, bye. Is asking, okay, is it because the segments sent by server after receiving fin may be dropped? Well, you know what? It is possible. Yeah, so the ACK to the fin back to the server might get lost. In that case, server might, yeah, retransmit the fin. Very good. You think you've got it. Good to know. Good to know that you guys are actually thinking serious about the questions there. But don't neglect to get lunch.